Um, Hello, it's a pleasure to be here. I hope you have my screen. Do you have it?
Yes, we can see and we can hear you.
Okay, thank you very much. It's a pleasure to be here. I would like to thank the organizing committee for managing this excellent conference. I'm going to present a study on radical pairs that, looking from another point of view, from a normal aspects of radical pairs, that is new, but it's actually simple and can enlighten our ways to see another aspects of the problem. I'm going to present this study on behalf of our quantum biology team in Research Center for Quantum Engineering at Sharif University of Technology. Okay, it's a relief that we have extensive talks on radical pairs, so there is no need for me to talk about biological aspects of the system. I'm going mostly to speak of the physical and mathematical aspects of radical pair mechanism and ignoring biological aspects of it. But it's not bad to have an overview on how the mechanism works. Magnetically sensitive reactions always include radical pairs, but we should know that these radical pairs should be in a non-equilibrium, short-lived transitional states, because this is an essential condition, because if we do not have this condition, the effect of the huge molecular Coulombic interactions nuclei will completely outshadow the Zeeman effect and the effect of weak magnetic fields. So we cannot actually observe the effect of something like Earth's magnetic field that is so weak on the evolution of the system. Normal approaches to radical pairs actually is a kinetic approach and is study the concentration of the product through the evolution of time. So it's engaged with the yield of singlet states and triplet states of the radical pairs. However, when we are in this non-equilibrium transitional states and we ignore the Coulombic interactions, we can really write the Hamiltonian in a simple form that have two major terms. One is hyperfine interaction, that is actually the coupling between nuclei spins and electron spins. This is mostly important because it creates an anisotropic environment that works like an engine for the radical pair reactions and start the time evolution of the system. And the other one is quantum Zeeman effect that engages the magnetic weak field to the spins of the electrons. These systems mostly, as I said, studied on the yield of singlet and triplet states, and it's acceptable because when you only engages the spin, what observable you have to study. You must actually measure the population of the singlet and triplet states. This Hamiltonian may have 2 or 3 terms, more or less, like dipolar or dipolar coupling, like spin-spin coupling, that and exchange coupling, that more or less they are cancel each other, and these 2 terms are more important. Here we are going to take a look in a newer direction. But how about we have more observables to measure in this system? Here we are going to add another term that is a famous spin-orbit coupling that couples the angular momentum of the electrons to its spin. This term has a negligible value according to the order of the magnitude, according to the Zeeman effect and hyperfine effect. But the work that actually it's do, it couples the spatial states and the spatial properties of the system to the spin of the system. You know, the dynamic of the system is not going to change if we include the spin orbit term or not. but when we include it, we have access to the observables that are related to the spatial properties of the system. Okay, this creates more opportunity for physical signaling in a radical paired magnetoreception. For example, say in this scenario, you can go with everything, any observable that work with the spatial properties of the system. We chose radical pairs that is actually work pretty well and has a clear results that we are going to talk about it. As you see, we write the operator for dipole moment and use the famous annihilation and creation operators to for the position operator. And using rotating wave approximation to only limit the system in ground state, in double state, in ground state and excited state of the system. These are the spatial state of the system that are coupled to the spin states, which are singlets and triplets or any superposition of singlet and triplet states. From now on, I'm going to show you a bunch of figures and graphs to see the results of our computations, mostly on the expectation value of dipole moment observable, and ignore the equations. Okay. We considered a batch of 10 to the power of the 6 radical pairs oriented in a specific direction. This is not this is a good, actually, assumption, because if you are looking at the problem from the kinetic point of view, you also need to assume this assumption that the radical pairs are oriented in a specific direction. Okay, if we sketch the evolution of expectation value of the dipole moment through time, in different inclination angle, actually theta is the inclination of angle of the Earth magnetic field due to our radical pair, relative to our radical pair. We will see that there is a periodical evolution of radical dipole moment that differs in any inclination angle. For samples, I just bring theta equals to pi and theta equals to pi over 4. This period have two periodic time. One is near 1 exponential to the -6, about 1 microsecond, and the other one, the huger period, is about 1 millisecond. Okay, this is just sample graphs here. As we see, the expectation value of dipole moment, according to the coupling between the spatial states and spin states through radical spin orbit coupling, completely varies between different inclination angle. Though studying dipole moments, I should note that this is for isolated system. We didn't consider environment yet. It's completely related to the inclination angle of the Earth's magnetic field and can be a criteria as a signal for magnetosensitivity or creating a sensor that is sensitive to weak magnetic fields. If you look for when we consider 10 to the power of 6 dipole moments, I sketched the dipole moments in Dubai. It's the differences between the changes in inclination angle is quite large, and I think it could be observable experimentally. Okay, here I sketched the changes in expectation value of dipole moment versus theta at 10 microsecond. It has a periodic change. This pattern, if we are going to choose dipole moment as a criteria or as a sensor to magnetic field, this pattern is what we are looking for to observe the weak magnetic field. It's completely related to theta, and it has a periodic. But if you have an attention here, we can see that this system cannot differs between like 0 theta equal to 0 and theta equal to pi. You know, it cannot actually make difference between North Pole or South Pole. Okay, so if this system is going to work as a magnetic sensitive, we're gonna need a system for actually point out the direction. Okay, this is the sensitivity of the dipole moment to the inclination angle. We are going to look at sensitivity and relativity to the magnitude of magnetic fields. The interesting aspect of looking at dipole moments of the system is that it has a reverse relation to the order of the magnitude of the magnetic field. From the equator to the poles of the Earth, the magnitude of magnetic field is going to change between 25 microtesla to 46 microtesla, if I'm correct. And we see when the magnitude actually decreases, the changes in dipole moment actually increases in this system, and it's had a reverse effect on the dipole moment. This will have some interesting consequences that we'll see in next slides. Okay, here, yet in an isolated system, because of the great dependency of dipole moment to the inclination angle and the magnitude of magnetic field, we somehow could create a magnetic map. You know, I saw in a study, I forgot to address the article here, that if we have the magnitude and inclination angle of magnetic field and also have the direction to the North Pole and South Pole, we can have a complete magnetic map for magnetic navigations. Okay, let's now add the effect of the environment. Okay, to add the effect of environment, we are using Lindblad equation, master equation. It's not a perfect master equation for biological systems, but actually it's not bad because it's somehow a worst case scenario. It's just get the system and put it in the thermal bath, all of it. So in each aspect, we will see the effect of the environmental dissipation on the system. I bring a figure, for example, here. From now on, the left figure is for theta equal to pi over 2, both systems. It's not corrected here. The actual effect of the environment is going to dissipate the system, create these oscillations and dissipate it to completely, actually, completely remove the coherence of the system through time. Now we are going to add the environmental effect to previous calculations. If we included Lindblad equations, we have this figure at a steady state. It means it passed the decoherence time. The environment had its complete effect, and there is no coherence in the system. However, after that, when the system reaches a steady state situation, the dipole moment, the value of the dipole moment is still sensitive to the inclination angle. It reduces from the its sensitivity, somewhat reduced from the isolated situation, but in this case, we also still have sensitivity to the magnetic field. This also could show that even when long-lived quantum coherence can have no rule in this point of view to the radical pair mechanism. Okay, let's have the system here. Now let's add time-dependent magnetic noise to the system. Okay, there are so many behavioral studies, including time-dependent magnetic noise. These studies could help us that our direction in maybe theoretical direction on explaining the magnetic sensitivity in radical pair system is going in the right direction. Is it in accordance with behavioral studies or not? Okay, but this is a simple sketch in theta equal to pi over 2 that shows when we have a time-dependent magnetic noise field plus to the weak Earth magnetic field, how our evolution of the dipole moment, expectation value of the dipole moment, is going to change through time, and it has its disturbance on the pattern of the system. I have to note that the left picture have no magnetic noise, and the right picture have a magnetic noise perpendicular to the Earth's magnetic field. Okay, from now on, I'm going to define this observable PDIF. It's equal to the dipole moment where we have no magnetic noise minus in a case we have the magnetic noise. When we sketch PDIF, it's going to be easier to observe the effect of magnetic noises. Okay. In these two pictures, we have PDIF at theta equal to pi over 2 for different magnitude of the magnetic field noise. As we can see in a perpendicular case, when the magnitude of magnetic field increases, we have more disturbance to the system, and the expectation value of the magnetic dipole moment is going to differ more from a mode that we have no magnetic field noise. Otherwise, in a parallel case, when the magnetic field noise is parallel to the Earth's magnetic field, the effect of the magnitude of is less than in the perpendicular, is actually much less than in the perpendicular version. We will see here, okay, that in the perpendicular version, actually the disturbance is quite huge and may perturb the dipole moment-based navigation system. Okay, let's look at the changes of the frequency of the magnetic field noise. Actually, the effect of the frequency is much less than the effect of the magnitude of the noise, but actually here is a reverse. When the frequency is going increases, like the purple ones and the red ones in this figure, the noise is going to be negligible and we can ignore it. Okay, even in higher magnitudes, but the frequency is also high, the system is getting no disturbance. This is for the perpendicular term. For a parallel one, it's actually shows no differences. PDIF is almost equal to 0 for the parallel case. Okay, I'm still at theta equal to pi over 2 because it has the clear pattern relative to the other thetas that you can observe the effects better. I chose this for all the figures in this study. Okay, we chose the changes of the dipole moment versus theta as our criteria of sensitivity to the magnetic field. In a perpendicular case, when we sketch the dipole moments in 10 microseconds, versus theta, actually the pattern is going to change in about near theta equal to pi. This shows that in high magnitude of noise we will see disturbance in our magnetic sensitive navigation system. But in a parallel case, actually it has almost zero effect. When our noise is parallel to the magnetic field, the system works correctly. This actually we will talk that is accordance. It is in agreement with the behavioral studies of navigation system based on vertical pair on beds. Okay, let's have a look on frequencies of the magnetic noise. As we see, the effect of frequency is much less than the effect of the magnitude. And when we look at it as the pattern of the dipole moment through theta, it almost, again, have no effect. In parallel one, it has completely no effect. But in a perpendicular case, we can see the differences. But as I see, it cannot disturb the system. Okay, let's add the environmental noise to the magnetic noise field and see all the noises, what all the noises would do to our system. When adding the environmental effects to the magnetic noise field, it seems it completely disturbs the system. It actually amplifies the effect of magnetic noise fields, the presence of environment. This is the case in 10 microseconds, and if we let it to reach the steady state, we see that it disturbs the pattern, and we should expect perturbation in navigation systems in such cases. Okay. When we studied, I didn't study the parallel case more because we have seen that in a parallel there is no effect of the magnetic noise field. So I continued with the perpendicular one. If we have the environmental noise in some other angle relative to the Earth's magnetic field, it can be analyzed in its perpendicular and its parallel aspect, but we are going to look in a special case that is 24-degree. The magnetic noise field is 24-degree relative to the static magnetic field because it's been reported that at this angle, the system, the beds, actually behavioral studies, show the most disturbance. We expect that because of the perpendicular one, we expect normally that we have the most disturbance and when the magnetic noise field is perpendicular to the Earth's magnetic field. But as we see before, the relation between the order of the magnitude of the magnetic field and evolutions in and the value of the dipole moment is actually a reverse. So in 24-degree, we see more disturbance that is in complete agreement with behavioral studies. If we look at the pattern of the changes in dipole moment versus theta, we clearly see a huge change, large changes in the pattern that is completely perturbed. And if we have a closer look, when we studied the perpendicular case, we couldn't see the difference in patterns in nanoteslas and a little differences in microtesla. But when we look at 24-degree, even in 100 nanotesla, it can make a difference between the pattern of the dipole moment to the system. Okay, we studied here dipole moment. This is a very recent study, and we are planning for having more theoretical and experimental work on this system.
Thank
But
you
this
very
is not the
much.
last word. Okay, okay.